All right, I'm going to explain a bit about vortices and, the math behind it and that sort of stuff. So, all right, let's just start with an example. I think that would be best. So you've got a channel, so X and Y coordinates. Let's say it's pressure-driven flow. So dP dx. It will look like that. Zero velocity here, and then max velocity in the middle. Yeah. So what would the vortices look like? So the way, well, I'll show the visual way and then I'll show the math way. So visually, if you drew like a little element, like a box right there, which way would it spin? Would it spin like that, or would it spin that way? So actually, I could have left those there, but anyways, if I redraw it right here, it's a rectangle, but it doesn't matter. On this side, it's being pulled with a velocity that's, let's say, that long. This side, it's being pulled with a velocity that's gonna exaggerate it. I'm gonna exaggerate it like a lot. That's slightly less, because right there versus right there. So it's being pulled with a higher velocity on the top surface and a lower velocity on the bottom surface. So it will want to rotate this way, and it will spin. That's pretty much vortices. You could literally end the video now and you'd be good. But let's talk about the math behind it. So the equation is vorticity equals grad cross u hat, and u hat is u, v, and w. It's all three of them. So this breaks out to the determinant, I've probably lost all of you by now, of I, J, K. So those are the three directions, d, dx, d, dy, d, dz, u, v, w. That's what it is. So what is the determinant? It's cross out those two and multiply by I. So it would be dw dy minus dv dz I minus dw dx minus du dz. I think that's right. And this will be j plus dv dx du dy. Is that right? I think that's right. So, what does this mean? So, all right, back to this example. I did the math, and the flow profile, if you assume x and y, if you assume y is 0 at the bottom, some people assume y is 0 in the middle. Either one's fine. You'll get the same answer. I chose that one. Well, you get different answers, but they'll mean the same thing. So if you do it with this method, you end up with the equation using Navier-Stokes of 1/2 mu dp dx times y squared minus hy. Cool. So let's look at the vorticity. First of all, we don't have w because I didn't write the assumptions here, but our assumptions are w is 0, it's 2D. So one of our assumptions is 2D. I'll just write that somewhere here. 2D. So it's 2D, so those go away. Those go away. You're left with this one. Cool. So then dv dx, and if you did the problem, you would find out that v is 0. Because if you do one of the, no, if you do the continuity and then you use the boundary condition, v at 0, at y equals 0, you'll get that v is 0. So you got v is 0 and u is this big thing. So dv dx, derivative of 0 is 0. So it would be 0 plus du dy. And I'm gonna lump this all up and call it a, because it doesn't matter. So it would be, and then if I rewrite it, it would be ay squared minus, you know what? I'm gonna lump it all up and call it 1. So that way we're left with y squared minus hy. I just don't want to write it. You can multiply it all by it. It literally won't matter. But I'm just going to call it 1, so I don't have to write as much. So if you take the derivative of that with respect to y, you'll get 2y minus h. Cool. Well, what does that mean? It means that if you are, I'm going to erase this guy. If you are, by the way, h is h. My h's are always that. If you're below h over 2, where do I write it? I write it right here. H over 2. If you're below it, so let's say you're at h over 4. All right, let's plug that in. Let's see what we get. W h equals 2h over 4 minus h. And that would be h over 2 minus h, which equals negative 1/2 h. Magnitude doesn't matter. The fact that it's negative matters. So what does that mean? That means that, let me draw something else here. Yeah, that's out of the page. Z is positive when it's pointing out of the page. So k, if the number for k is positive, it points out of the page. We got a negative number. We got a negative. So that means if we point our thumb into the page, our fingers rotate clockwise. So the little element should want to rotate that way, which is what we said before. That is literally what we said before, just by drawing this box and drawing the arrows around it. Likewise, if we say h, 3h over 4. So it's above h over 2, but it's below h. We will get 2, 3h over 4 minus h, which equals 6h over 4 minus h, which equals 3 2h minus h equals positive 1/2 h. And it's positive. So that means if we point our thumb out of the page and rotate our fingers around, it goes that way. That's literally it. That's all vorticity is. Yep, that is literally it. Cool beans. All right, I want to do one more example, but in the radial direction. Okay, so let's say you've got, again, oh, dang it, man. Okay, let's say you've got a pipe this time. And it's pressure driven again. So dp dx. There's center line, and it'll look similar. The equation won't be the same, but it'll look similar. You'll have it like that. And you will expect to have the vorticity spin it like that. And it will, but the math for it is a little bonkers. Dang, I don't have it written out super nicely, but you end up using this exact same determinant approach. You end up dw dr in the j direction. So let's draw our axis. W, this will be u and the r, w and the z, and out of the page will be I don't want to draw it there. I want to draw it up here. Will be v theta. So there we go. And this is I, this is j, this is k. Similar to how up here I was x and j was y, and k was z. Cool. Now's the interesting part. So I did the math again, and we get w as a function of r is 1/4 dp dz r squared minus big R squared. And big R is just that. So what does this tell us? Again, I'm going to lump all these together and just call it 1. And so we'll take the derivative of r squared minus r squared, and we get 2r minus r squared. Is that right? No, this literally goes away. We just get 2r because this isn't a function of r. It's a number, which kind of sucks. I drew both as r, but I do, and I like it, so I'm going to stick with it. The interesting thing here, well, before, our equation depending on what we put y as, it would either be positive or negative. We could get negative or positive if we're above or below the center line. But here, it's positive all the time because R ranges from 0 to big R. So we just get a positive number all the time. So how does that make sense? Well, if we look at this, so if we're up here in this area and we look at V, it's positive, so we stick our thumb out of the page and rotate. We'll get this. We'll get this. So this is W equals positive. So that makes sense. The top half makes sense. But now the bottom half, it's technically not a bottom half. It's all the same thing. So if this is U, that's your I, and you're looking that way, you will see, what will you see? You'll see a circle. U and V will point that way, V. So again, you stick your hand out, you stick your hand the direction of V, rotate it, and you'll get what we got. But if you rotate the U vector to the bottom half, so down here, like down there, if you rotate it, that's still, I'll draw it on the other side, U of R, but now your V points that way. It points into the page, even though it's still positive. So you stick your thumb into the page, you rotate it, and there you go. Yeah, that's about it. Cool beans.